Picture this. Your 10-year-old wants to measure air quality around the neighborhood, contribute real data to actual scientists, and maybe even help solve environmental problems. Great. But when you start looking at platforms, you hit a wall. Arduino, microbit? Everyone's got an opinion, and half the advice online assumes your kid's already fluent in C++. I'm Lakshmi Venkataraman, a National Board Certified Middle School Science Educator with a master's in curriculum and instruction, and I've watched hundreds of sixth graders wrestle with this exact choice during watershed monitoring projects. Here's what actually matters when you're picking a platform for citizen science. You're listening to the STEM Lab podcast. Quick heads up, everything you're about to hear, all the research, the data, the recommendations, that's 100% human verified and written by real educators. But the voice you're hearing, that's AI generated. Just wanted to be upfront about that. Now, if you've been tuning in for a while, I really appreciate you showing up episode after episode. And if you're new here, welcome. I'm glad you found us. We release new episodes every Monday, Wednesday, and Friday, breaking down real questions parents face when they're trying to build meaningful STEM experiences at home. Today, we're tackling a big one, Arduino versus microbit for citizen science. Let's dive in. For most families building environmental monitoring and data collection skills, the BBC Microbit version 2.2 delivers a smoother entry point into citizen science. Check the link below to see the current price. But Arduino becomes essential once your young researcher tackles advanced multi-sensor deployments and long-term field studies. This comparison breaks down exactly when each platform makes sense for real-world data contribution projects. Choosing between Arduino and microbit for citizen science means understanding your child's current coding fluency, the complexity of the environmental questions you're investigating, and whether you're building toward professional-grade research tools. I've watched this decision play out hundreds of times, and the right choice always comes down to three factors: programming prerequisites, sensor ecosystem maturity, and data management pathways. Now, let's talk about what separates these platforms in practice. Arduino's Uno R4 Wi-Fi runs on text-based C++ and requires understanding things like data types, library imports, and serial communication protocols. Microbit, on the other hand, uses block-based make code or Python, and text coding is completely optional. For sensor options, Arduino gives you access to over 10,000 third-party sensors with industry-standard protocols. Microbit offers around 200 education-focused sensors, mostly using proprietary connectors. Power management? Microbit has it built in and can run 72-plus hours on 2 AAA batteries. Arduino requires you to design external battery regulation circuits for field deployment. When it comes to getting data out, microbit has built-in data logging to CSV with direct Bluetooth transfer to smartphones. Arduino needs you to code everything: SD card logging, serial monitor exports, cloud APIs. The learning curve to your first deployment runs about 8 to 12 weeks with Arduino if your child already has Scratch or Python experience. With microbit, you're looking at 2 to 4 weeks from absolute beginner. Cost-wise, a functional field station runs $65 to $85 with Arduino once you factor in the board, sensors, enclosure, and power. Microbit comes in around $45 to $60. Moving on to programming prerequisites and skill scaffolding, the gap between Arduino and microbit isn't subtle. It's a conceptual chasm that determines whether your child spends their first month wrestling with syntax errors or collecting actual environmental data. Arduino platforms run on a C++-based language. That means understanding data types, library imports, serial communication protocols, conditional logic structures. Even with the Arduino IDE's MakeCode extension, which came out in late 2025, you're ultimately translating visual blocks into text code that your young researcher has to debug when sensors misbehave. The Arduino Uno R4 Wi-Fi ships with sample sketches for common citizen science tasks like temperature logging and light measurement. Check the link below to see the current price. But adapting those examples requires comfort with curly braces, semicolons, variable scope. These are concepts that typically emerge around age 12 to 14 after kids have successfully completed block-based robot programming. I've seen this hurdle derail promising watershed monitoring projects. A 7th grader pulls together a gorgeous turbidity sensor housing, writes 90% of the Arduino sketch correctly, but abandons the entire project over a single missing semicolon in line 47. The cognitive load of simultaneous scientific questioning and syntax troubleshooting overwhelms the working memory capacity of most middle schoolers. The microbits make-code environment scaffolds this complexity beautifully. Your child drags on-button A pressed blocks, snaps together sensor reading commands, and sees immediate visual feedback on the LED matrix, all while building genuine data literacy skills through citizen science. When they're ready for text-based coding, MakeCode's toggle view feature shows the equivalent Python code side by side with the blocks. It creates a bridge rather than a cliff. The skill-outcome difference matters for sustained engagement. Arduino demands prerequisite programming fluency before scientific inquiry begins. Microbit allows scientific inquiry while programming fluency develops. For families following a progressive STEM learning path, Microbit aligns with ages 8 to 13, while Arduino becomes appropriate around age 13 to 16 after successful Python experience. Now, sensor ecosystem and measurement capabilities. When you're contributing real environmental data to projects like NASA's GLOBE program, measurement accuracy and sensor diversity directly impact your scientific contributions' value. And here, the hardware ecosystems diverge dramatically. Arduino's massive third-party sensor library includes industry-standard options like the BME 680 air quality sensor, which measures VOCs, temperature, humidity, and barometric pressure simultaneously. There's the AS7265X spectral sensor with 18-channel light analysis from UV to near-infrared. Research-grade turbidity sensors that match USGS stream monitoring protocols. These sensors communicate via I2C or SPI protocols, the same interfaces used in university research equipment and commercial environmental monitoring stations. When your teenager's air quality data feeds into the EPA's air sensor toolbox, they're using the same BME 680 sensor deployed in professional low-cost monitoring networks. The SparkFun environmental combo breakout is a good example of Arduino's research-grade pathway. Check the link below to see the current price. It outputs ECO2 and TVOC readings alongside temperature, humidity, and pressure, all logged to an SD card with timestamps accurate to within 2 seconds over week-long deployments. That temporal precision matters when you're correlating pollution spikes with traffic patterns or industrial schedules. Microbit's sensor ecosystem prioritizes educational accessibility over measurement diversity. The official Microbit Environmental Science Kit from Kitronic includes soil moisture, UV index, and temperature sensors with color-coded connections that eliminate wiring errors. Check the link below to see the current price. It's a thoughtful design for 9-year-olds, but limiting for sophisticated multi-parameter studies. You're working with roughly 200 compatible sensors versus Arduino's 10,000 plus, and many microbit sensors use proprietary edge connectors rather than industry-standard protocols. However, this constraint creates an unexpected advantage for certain citizen science projects. Microbit sensors ship pre-calibrated with age-appropriate measurement ranges. The Kitronic air quality sensor, for example, displays a simple 1 to 5 air quality index rather than raw parts per million readings. That reduces calibration complexity for elementary students while still contributing useful categorical data to community air quality mapping projects. The measurement capability gap widens with multi-sensor deployments. Arduino handles 8 simultaneous analog sensors without performance degradation. Microbit struggles beyond 3 sensors due to limited I/O pins, 3 dedicated edge connector zones versus Arduino's 14 digital and 6 analog pins. For watershed monitoring projects tracking temperature, dissolved oxygen, pH, and conductivity simultaneously, Arduino becomes non-negotiable. Let's get into power management and field deployment durability. Real citizen science happens outdoors, often in locations without wall outlets. Power architecture is the unglamorous factor that determines whether your child's data collection spans hours or weeks.
The microbit version 2.2 treats battery operation as a first-class use case. Its integrated power management circuit regulates voltage from 3 volts to 3.3 volts efficiently, running 72+ hours on 2 AAA batteries during typical environmental sensing. That's temperature reading every 5 minutes, LED display off. The onboard accelerometer enters sleep mode automatically between readings, and the Nordic processor draws just 3 microamps in system off mode. For a weekend air quality monitoring deployment in your neighborhood park, you pack the microbit in a waterproof case Thursday afternoon and retrieve reliable data Sunday evening without battery anxiety. I've deployed microbit weather stations with my 6th graders for 3-day outdoor education trips, and the batteries outlast the camping snacks every single time. That reliability matters enormously for maintaining scientific enthusiasm. There's nothing more deflating than hiking to your monitoring site to discover dead batteries captured 0 data points. Arduino requires manual power management circuit design unless you invest in purpose-built shields. The Arduino Uno R4 Wi-Fi runs on 5 volts, but your sensors likely need 3.3 volts, requiring voltage regulators. Battery operation demands understanding milliamp-hour calculations, sleep mode programming, low-power sensor selection. The Adafruit PowerBoost 1000C handles USB battery pack regulation elegantly. Check the link below to see the current price. But now you're managing a 3-component power chain: battery to boost converter to Arduino to sensors. Each connection point introduces potential failure. For field deployments lasting multiple weeks, say monitoring seasonal temperature shifts in a stream restoration area, Arduino's power flexibility becomes an asset. You can connect solar panels, implement sophisticated sleep schedules that wake sensors only during daylight hours, use external real-time clock modules for precision timestamp correlation. The learning investment pays off when your high schooler contributes temperature data spanning entire migration seasons to fisheries research databases. The durability factor extends beyond power. Microbit's sealed edge connector design resists moisture intrusion better than Arduino's exposed pin headers. I've recovered microbits from rain-soaked backpacks that booted normally after drying. Arduino's open architecture offers easier repair when components fail. You can swap a damaged sensor without replacing the entire board, but it requires more meticulous weatherproofing. Next up, data management and research contribution pathways. Collecting environmental measurements matters only if that data reaches researchers who can analyze patterns, and the data export pathways reveal different philosophies about who handles the technical complexity. Microbit's MakeCode environment includes built-in data logging that automatically timestamps sensor readings and exports clean CSV files via USB connection. Your 10-year-old drags a log data block into their temperature monitoring program, runs the microbit for a week in the backyard weather station, then plugs it into the family laptop and sees properly formatted spreadsheet data ready for graphing. No serial monitor commands, no parsing raw text streams, no "why are all my timestamps showing as 0" debugging sessions at 8 p.m. on Sunday before the science fair. The best microbit citizen science kits leverage this accessibility for genuine research contributions. The National Phenology Network's Nature's Notebook project accepts temperature and first bloom observations logged via microbit, and the SciStarter platform lists 30-plus microbit-compatible projects, ranging from backyard bird counts to urban heat island mapping. The data contribution barrier sits exactly where it should for elementary and middle school researchers, not in the technical export mechanics, but in observation quality, measurement consistency, and research question formation. Bluetooth data streaming adds another pathway. The official Microbit app pairs with iOS and Android devices, letting students download datasets directly to smartphones in the field. I've watched 8th graders monitoring pond water quality transfer their dissolved oxygen readings to phones, photograph the collection site, and upload both to community watershed databases within 5 minutes, all without touching a computer. That immediate feedback loop reinforces the connection between their measurements and real scientific value. Arduino's data management requires explicit programming of every export step. You write code to initialize SD card communication, format timestamps, define CSV delimiters, handle write errors, and manage file naming conventions. The SparkFun OpenLog simplifies some complexity by handling serial to SD conversion automatically. Check the link below to see the current price. But you're still working in a text-based environment where a single misplaced quotation mark corrupts an entire dataset. This complexity creates opportunity. High school students preparing for research careers need experience with programmatic data management, the skills that transfer directly to university lab instrumentation and professional environmental monitoring. When your 16-year-old programs their Arduino weather station to post JSON-formatted data to a cloud API every hour, they're practicing the exact workflow used by NOAA's distributed sensor networks. That's career-relevant skill building that microbit's friendly abstractions deliberately avoid. The research contribution ceiling differs substantially. Arduino-generated datasets integrate seamlessly with platforms expecting raw sensor data, the Purple Air Network for air quality, the Community Collaborative Rain, Hail, and Snow Network for precipitation, the GLOBE program's advanced protocols. Microbit data works beautifully for educational research platforms and community science projects with simplified data requirements, but sophisticated multi-parameter studies eventually demand Arduino's programmatic control. For families building toward progressive research skill development, I recommend starting citizen science projects on Microbit around age 9 or 11, then transitioning to Arduino around age 14 to 15 when students have accumulated enough Python experience to handle text-based environmental monitoring code. That progression mirrors the developmental sequence from question formation to instrumentation design that defines actual scientific practice. So who should choose Microbit? Choose Microbit for ages 8 to 13 when you're prioritizing rapid deployment, building foundational data literacy, and contributing to educational citizen science projects that value participation breadth over instrumentation sophistication. The platform excels when your child's scientific curiosity currently outpaces their programming fluency, and you want immediate environmental investigation rather than delayed gratification after months of syntax practice.
Microbit makes particular sense for families who want physical computing to scaffold rather than obstruct scientific questions. If your 9-year-old asks, "Why is our backyard hotter than the park?" they can answer that question with actual temperature data this weekend using Microbit versus 3 months from now after Arduino programming tutorials. The platform also suits families prioritizing classroom alignment and peer collaboration. Many school districts have standardized on Microbit for middle school science, meaning your home citizen science projects can extend classroom investigations seamlessly. Your child's Microbit weather monitoring code translates directly to group projects without platform friction. Online communities like the Microsoft MakeCode forums offer age-appropriate peer support rather than the advanced maker discussions dominating Arduino spaces. Who should choose Arduino? Select Arduino for ages 13 to 18 when your teenager demonstrates solid Python or Scratch proficiency, investigates multi-parameter environmental questions, and aims to contribute research-grade data to professional scientific networks. The platform becomes essential when sensor diversity matters more than deployment simplicity, and when building career-relevant instrumentation skills justifies the steeper learning investment.
Arduino particularly suits families following a robotics to citizen science learning pathway, where students transition from educational platforms like Lego Mindstorms toward industry-standard tools. If your 15-year-old successfully programmed Vex robots and wants environmental engineering experience, Arduino provides the instrumentation foundation used in actual water treatment facilities, air quality monitoring networks, and climate research stations. The platform also makes sense for long-term, high-complexity deployments where power optimization, sensor calibration, and data pipeline customization matter more than weekend project accessibility. Students designing months-long stream temperature monitoring for salmon restoration, multi-location air quality networks measuring ultrafine particulates, or soil moisture arrays testing irrigation efficiency need Arduino's flexibility and professional sensor compatibility. Let me tackle some frequently asked questions. Can a child transition from Microbit to Arduino for citizen science without starting over completely? Yes, the conceptual frameworks transfer beautifully, even though the syntax changes dramatically. Your child's understanding of sensor reading loops, conditional data logging, and measurement interval timing remains completely relevant when moving from MakeCode blocks to Arduino C++. The technical skills that don't transfer, like I2C communication protocols, library management, serial debugging, are genuinely new territory for both platforms, so Microbit doesn't create false knowledge that needs unlearning. I recommend making this transition around age 13 to 14 after at least 3 successful Microbit data collection projects. Time it to coincide with introduction to text-based Python to reduce the cognitive load of simultaneous syntax acquisition and scientific investigation. Do citizen science platforms like Globe and SciStarter accept data from both Arduino and Microbit equally? Most platforms care about measurement accuracy and methodology documentation rather than the specific hardware generating the data, but practical barriers exist. Projects requiring specific sensor calibration, like Globe's air temperature protocol demanding plus or minus 0.5 degrees Celsius accuracy, favor Arduino's compatibility with research-grade sensors. Projects emphasizing participation breadth and educational engagement work equally well with Microbit's simpler instrumentation. The critical differentiator is data format. Platforms expecting manual data entry, observational forms, photo uploads work identically with both. Platforms requiring automated uploads via APIs or direct database connections favor Arduino's programmable export capabilities. Always check the specific project's technical requirements before purchasing sensors.
Is the cost difference between Arduino and microbit significant enough to influence platform choice? The purchase price gap is modest, around $25 for a starter board, but total cost to deployment varies substantially depending on project complexity. A basic temperature and humidity monitoring station costs roughly $45 to $60 with microbit. That's board, environmental sensor, battery holder, weatherproof case, versus $65 to $85 with Arduino. Board, equivalent sensors, power regulation, SD hogging shield, case. However, Arduino's sensor ecosystem offers dramatically better value for multi-parameter studies. A single $35 all-in-one environmental sensor breakout for Arduino often replaces 3 separate $20 microbit sensors, reversing the cost equation. The larger financial consideration isn't initial purchase, but subscription requirements and consumable costs. Both platforms operate subscription-free for core functionality, though cloud data services like Adafruit I/O charge for high-frequency logging above free tier limits. For families building long-term progressive STEM learning paths, I suggest budgeting $150 to $200 annually for sensor upgrades and expansion modules, regardless of platform. Treat citizen science instrumentation as a renewable learning investment rather than a one-time toy purchase. Here's the bottom line. The Arduino versus microbit citizen science decision ultimately reflects your child's position on the continuum from scientific curiosity to research capability. Both platforms serve distinct, valuable roles in developing environmental literacy and data contribution skills. For most families starting citizen science with ages 8 to 13, microbit delivers faster deployment, lower frustration, and genuine scientific engagement without the programming prerequisites that delay Arduino projects for months. The platform scaffolds authentic research contribution while programming fluency develops in parallel, which aligns perfectly with middle school developmental readiness and next-generation science standards emphasis on investigation before instrumentation. Arduino becomes the essential next step around ages 14 to 18 when your teenager's scientific questions outgrow microbit's sensor ecosystem, when multi-week field deployments demand sophisticated power management, and when contributing to professional research networks requires programmatic data pipelines. The platform prepares students for the instrumentation reality they'll encounter in university research labs and environmental careers, making the learning investment directly transferable to STEM futures. The best progressive pathway mirrors natural skill development. Start environmental investigation with microbit around age 9 to 11. Accumulate successful data collection projects that build research confidence. Develop text-based Python fluency through parallel coding progressions. Then transition to Arduino around age 14 to 15 when sophisticated multi-sensor questions emerge naturally from prior investigative work. That sequence prioritizes sustained scientific engagement over premature technical complexity. It's the same principle I've watched successfully guide hundreds of middle schoolers from backyard weather curiosity to meaningful watershed research contributions. That wraps up this episode of the STEM Lab podcast. Thanks for listening. New episodes come out every Monday, Wednesday, and Friday, so there's always something fresh if you're looking for the next step in your family's STEM journey. If this episode was helpful, I'd really appreciate it if you left a 5-star rating and a quick review. It honestly makes a difference. It's how other parents find the show when they're searching for this kind of guidance. And go ahead and subscribe or follow so you get notified the second a new episode drops. I'll see you next time.